Francois, thanks so much for inviting me here. What a great meeting. I love building robots, but I'm personally not all that great at building things. So at Boston Dynamics, we have a team of robot maniacs, people who love to build cars and fashion and electronics, naturally, and all kinds of mechanical designers. And it's a real pleasure. And today, I'm just going to give you a little update on what we've all been doing there back in our office and lab and factory. But first, I'll tell you a little bit about our goals. Could I have the slides, please? Our underlying goal is to build robots that have the functionality of people and animals. That's a very high level of performance. It means having the mobility, the ability to get around in the world, the dexterity, and the perception of people and animals. Now, I'll start out by giving you a little demonstration. Aren't you impressed? You should be. It's amazing how easy it is for each of us to get around in the world. And here I am balancing. Okay, here, I'll up the ante. One leg. Okay? How about I'll do it dynamically? And that's really an amazing feat. And it involves my brain, my sensors, my physical body, all of those coordinated. Now I'll do a little manipulation demonstration. I'm going to use my hand. People are incredibly good at using their hands. I'm holding this little slide clicker. I can rotate it around in my hand. I could go the other axis around, and I can do that without looking. And it's all, again, because of the sensing in my hand, how good my brain is at interacting with my body, and planning and all those things come together to make it so we're so dexterous. And finally, perception. I mean, maybe that's one of the most amazing things. Here's a room with almost 2,000 people in it, and I can see every one of you. I can move around and still locate you. You're not a bunch of swimming pixels. You're people. I could probably, at least in the front rows, tell the men from the women, and I could tell how old you are and all that stuff. And it's just happening, apparently, effortlessly. So our goal is to build machines that have those kinds of capabilities at the level of performance. They don't have to look like people and animals. They don't have to work the way people and animals work, but we want to get that level of functionality. Now, that's a ways off. Not today, not even tomorrow, but I think sometime in our lifetimes that will be achieved. Here I have another little demonstration of what animals can do. Here's a couple of mountain goats. Look at this one's a baby, probably just a couple of months old. In fact, there's another one here that's even younger. And they're just fearless. And also, look at the grace and the subtlety and the dynamic motion of this animal. And this one has its whole life in its hands, or in its hooves, as it climbs. And one of the amazing things is that people have all these skills too. I assume you were out this morning climbing up on the Louvre and the other buildings around here to get some exercise just like that. Well, it looks insanely hard, but I believe we will be able to build machines that do these things. So I'm going to give you a status report. This is about 10 years ago. This is Big Dog. This is the first robot that Boston Dynamics made, even though some of us had been making robots before that. And this is a dynamic robot. It's balancing itself. It's got reflexes. It's responding to its motion in the world. That was slipping on ice. And in the ensuing years, using some of the results that we learned in developing Big Dog, we made a bigger version that's designed to carry 400 pounds out in all kinds of terrain. This robot doesn't have a driver. It's following a human leader through the bush and up in the desert. And here we're demonstrating the mobility that legs offer. This is in 10-inch snow in Boston, as you might expect. And that's one of the fastest-legged robots that's ever been built. It went about 20 miles an hour. We have another version that works indoors at about 30 miles an hour. And of course, there's a lot of dynamics and controls and mechanical design and construction that goes into these machines. So that's where we were a few years ago. And I'm just going to tell you a little bit about what our approach to this kind of work is. One of the things that I think is a little bit different about what Boston Dynamics is doing is we've been an R&D company for years. And that means we haven't built products. We've built demonstrations, and we've shown videos of the results, but we haven't built robots that we deliver to people. And that's a way to move very quickly, to keep advancing the technology. But now we are also developing some products. And I'll do a demonstration of a robot that we'll have available next year sometime, which is a shorter range thing. And I think it's a real challenge for our company to be able to do these two things at once, to keep the culture and the intellect and the focus on advancing to the far future of what robots can do, at the same time as we're doing all the practical things of cost reduction, reliability, focusing on what the user needs and adapting the technology for that. And so I hope you can stay tuned over the next couple of years to see if we're successful at doing those two things at one time. So here's a little picture of what that looks like. If this plot shows one skill, this is mobility, the ability to get around the world. Here's manipulation. As I said before, reliability, cost. There's a million things that could be on these axes. And the product world lives in close where the capabilities can be less. And then in the long run, we want to advance the technology out here. So if we do that, what kind of applications will robots be able to do? I think in the short run, there's applications like entertainment. Basically, robots can be used either just as themselves or dressed up as animals or for other things, where they'll be entertaining for people at theme parks and other kinds of things. And we're going to do a test of this out in the lobby later on this morning and see if you're entertained by our robot, which hasn't actually had any specific entertainment design put into it, which can also be done. Another application is commercial security. There's many people in the United States, there's about 1.25 million guards who patrol places just on a routine travel to a bunch of locations to see if anything's gone wrong or to see if there's any trouble. And we think robots can be used for that as well, and we're doing some experiments along that lines. And another place robots can be used is in emergency response, places where people shouldn't go or can't go. My partner and I visited Fukushima last year, and we went through 10 kilometers of ghost town where no one lives anymore, but they have people in suits, humans in protective suits, cleaning off the terrain. And I think robots should be doing that. And that's a case where you could even have remote control robots. They don't have to be as autonomous. They don't have to be as capable. So that's really a good application. But the next phase is going to do slightly more complicated, but also commercially valuable things, like handling packages in warehouses. I don't know exactly how it is in France, but in the United States, Amazon packages are getting delivered every day to not every house, but it feels like every house. And they're not the only ones. All their competitors are now starting to do that. And I think there'll be an opportunity both to manage the processing of the packages on the way to your house, and then eventually actually delivering them to your house. And I'll show you a little bit about work we're doing in that area. But I think the home run areas are a little further out. There's construction, which could be the tasks of building buildings. We're already starting to do some inspection of construction sites, which is a little bit like the security task, but in more complicated environments. But this is the holy grail, I think. That is the ability to help people who are disabled or elderly. Right now in the United States, I don't know the numbers for France, but in the United States, there's about 31 million people who spend about half of the work week helping either a relative who's disabled or some other invalid who can't take care of themselves. Now, some of you may think that you don't want your mother or your father to be taken care of by a robot. But let's do some homework. Go home tonight and talk to your mother and father and ask them, would they rather a robot take care of them, or would they rather you change their diapers if that's what's needed, or help them into the bathroom? I think there'll be a day when robots will be a more acceptable solution for many people in order to do tasks like that. The robots aren't ready for that. I'm not saying that they are at all. It's going to take some time, but I do think we'll get there. And this is one of the places this whole robotics community can aim, where it's, I was listening to the Blue Oceans talk yesterday. It's a place where there's no one doing it now, and I think there's a real opportunity to provide a service that's really needed, that's not going to displace others. Well, this is sort of a quick sketch of where I think some of the robots we've built are on this curve. These are the early robots we built at Boston Dynamics, and today I'm going to show you this one, and depending upon how my time holds up, I don't see the time counter. Oh, there it is. Depending upon how my time holds up, maybe I'll show this one too. And we're starting to press out of the immediate near-term circle and into the far term. And this is one that we're making into a product that will be available next year for certain kinds of applications, limited applications. So these are the 4 robots we're working on, and I'm going to give you a little rundown and tell you about, a little bit at least, about each one. So after building Big Dog, the one I showed earlier, we refined all of our techniques and our designs, and we built this robot called Spot. This robot has electric power, but hydraulic actuation. It weighs about 80 kilo. And here we're testing the idea of being able to deliver packages right to your home. Now, this is actually one of our employees' homes, and that's one of our employees' wives. But we've been testing it at many of our employees' homes. You know, in the Boston area, all the houses are different. There's many different kinds of stairways and access constrictions, so it's a real challenge. We've been getting to about 80% of the access places for about 20 of our employees' homes, so that's pretty good. Now, one of the things we do when we develop these robots is test them not the way you expect the situation to be, or the robot expects it to be, but in a disturbed way. And testing this way, where we disturb the robot, is one of the most important things we do. I know sometimes people think we're being mean to the robots or abusing them, but we're really not. We're really letting them get better and better at their tasks by understanding what their failures are. Here we've put an arm on a robot, and I'll talk about that a little bit later. And it's supposed to just open this door and go through, but here we're testing its ability when things don't go exactly as it's planned. I think this idea of testing is going to allow robots to become skilled enough and able enough so that higher level AI won't have to worry about all the details and be able to give them plans and instructions, and we'll be able to have high level AI, which is worrying about thinking and the big problems of the world, something that we really don't do that much of. And then our kind of AI or robotics, which is focused on how the system moves in the world around it, how it perceives the world, and then how it engages to perform tasks. And those two parts will interact the best when the low level is really capable and able to do what it's asked to do. So I'm going to say a little bit about how our robots work, just a word or two. I know a lot of people imagine that if you have a dynamic robot, you must have lots of complicated equations and, you know, brainy people who don't come out in the sun and things like that. And we do have those people, and we do have lots of equations. But at the heart of things, we also have some very simple ideas that let you understand how robots work in the world. One model is the model of the rolling egg, developed by some biologist maybe 50 years ago. And the idea is that when an egg rolls, Its energy goes up and down as the center of the egg goes up and down. Its energy also oscillates out of phase with that as its speed changes, because when it goes up, it goes slow, and when it goes down, it goes fast. And that's very much the way a person walks when their body goes up over their legs and their speed changes. So this is an interesting model, a very simple one, of how a person walking is. This is a bouncing ball. And when a person or an animal runs, they're really a lot like a bouncing ball. They have elastic things in their legs that they store energy in. They fly through the air, where they also have kinetic energy and potential energy of elevation. And the point is to think about the mechanical system, the energies that are stored in it, and coming up with a model for how all those pieces can interact to get the behavior you want, like walking and running and manipulation and other things. And there's other models here which we could, if you're interested, we could talk about out in the lobby. But another important component is not just to have these deep, simple models, but to have an architecture where you can put it all together. We use something called sequential composition. For those of you who know something about controls, you can see these funnels. The concept is that you can have the robot in a state of uncertainty, as water is when it enters a funnel, but when it comes out of the funnel, you know exactly where it is, and that's in the narrow part of the spout. And if you can string together a bunch of funnels to guide the system to where you want it to be in dynamic space, you can get a kind of control over it that's very powerful. And this model also lets you divide up the problem, which is a big, hairy, complicated problem that no one can understand, into pieces that individuals can work on. So our engineers work on separated parts of the overall robot problem, and that lets them work in parallel. It lets them work on simpler problems and get really very advanced solutions. So I think this architecture is really important for robotics. I know I'm not giving you enough detail to be able to take home and use it, but you can find out more about it. And I think that this kind of architecture is going to have more impact on robotics than even things like machine learning, which everybody thinks is the most important thing. I think that this kind of architecture will be a host where machine learning can have its influence through this kind of partitioning of a complex dynamic system. Next, let me tell you about Spot Mini. This is the robot that we have in pre-production right now and will have available as a product, mostly to businesses next year. I don't know how long it'll be till this will be something that individuals can buy or even afford, but we are cost-reducing it, making it more reliable, and the like. So Spot Mini, as its name implies, is smaller than Spot. It's all electric, which means it's very neat to have in your office or your warehouse. And this is not a real house. This is a mock-up of a house. Those aren't real people. Those are engineers. And this is just a place that we built in a warehouse where we can test the robot in its ability to go up and down stairs. The robot has sensors on it, so it's perceiving its environment and adjusting its behavior to accommodate it. So no one's driving the robot here. It's actually an autonomous run where it's sensing the stairway and going along a path. And here you can see the results of planning, using its vision to decide where is a safe place to put its feet, and then planning the motion of the body, the motion of the feet, so that it gets through. Here's another example where it's a very tight, constrained space. And here's a dynamic obstacle that the robot's moving around, so it has to plan very quickly. And once you put together all that planning and sensing and reflexes, the robot can go in a wide variety of unstructured environments, such as walking on this wall. Now, this is an ordinary chicken. But ordinary chickens are really extraordinary because they can stabilize parts of their body while other parts are moving. And the good news is that people are like this too. I can hold my hand still while I move my body around, and that allows me to do tasks such as this, where the robot is manipulating the world around them using their hand, even though their body is moving in a complex way. So here Spot Mini is opening this door, doing a complicated task. It's not strong enough to just pull the door open and go through, so it uses its foot to hold it. It's actually being courteous to this other robot, which doesn't have its own arm. So it's sort of a disabled robot, the other one. And here, once again, we are not being mean to Spot Mini. It is not upset or irritated, as some of you may think. And that guy is a very nice guy, and Andy. He's really helping the robot by challenging it to both perform its task in unexpected environments, no matter what happens. And it does go through the door, as I think you know. Now, we've designed Spot Mini to be a platform, which means that we're building basic functionality into the robot itself. It has sensors and computers and obviously its mechanism and a capability to move with great mobility through the world. But we're also providing features so that users can add their own hardware and their own software. And so we're calling this the Android of robots, because just like you can buy an Android phone and then write your own app that goes on top to specialize it for your particular function, we made Spot Mini so that users can put equipment, hardware, and software in order to specialize it for their own application. This is partly motivated by us not yet knowing what the killer app for robots is. We know some things that we have a pretty good idea they'll be useful for, but we're in that period when we need to advance the state of the systems and make them cheap enough and available enough so that others can experiment with them, and I'm sure people will come up with things we never thought of and develop them for that. So we made some progress with developing apps, and these are two apps that we've developed ourselves, so we haven't gone the step of having third parties. This is a navigation or a patrol route map app where there's a computer added on here that has a map of the world, which we achieved by just driving the robot through the world with a human driving it. And now the robot is going autonomously through this space, and it just goes over and over through where we told it to go, using the data collected from its onboard cameras to help it navigate. You can see the view from the onboard cameras in terms of the obstacles it sees, and that lets it see the stairway, decide where to put the feet as it climbs the stairs. The whole time it's balancing itself, it's picking footholds, it's doing some rapid computations, looking out in the future in time so that it doesn't bump into things. There's a lot of coordination that goes on. You can all do this, but you don't even think about it when you're doing it. But one of the cool things about robots is we have to address each of these problems ourselves and design the robot to do it. Now, you notice the robot's going down the stairs backwards. It turns out that a quadruped with this limited leg design has an easier time going down the stairs backwards than forwards. And there's even some dogs that have that restriction too. And then here again is the map that it's using for navigating. Again, the same kind of data that's used for obstacle detection, but here it's navigating. And that video is on YouTube if you want to see it. Here's another app where we have an outside computer that's coordinating the behavior of these multiple Spot Minis to do a manipulation task. So it's telling it to find the can. It's got a camera in the hand. And then here we have 4 spots all working together. They don't actually know about each other. The computer that's coordinating them is passing data back and forth, but they're each doing what they're told, which is to handle these things. So we have a Spot Mini here, and this is Seth Davis, the head of our field ops team. And he's going to bring Spot Mini out. We're going to bring it up on stage, but first we'll bring it over so you can get a better look. Some of you will get a better look. If you can't see it, they have a camera feed here. So this robot has onboard computers that are controlling all the coordination, the sensing. You see it go up the steps. It can see the step and adjust its footfalls in order to accommodate that. We'll do that again when we come up on stage. And Seth is giving some high-level instructions. There's a radio connection. Seth's standing here in the front. And he's giving high-level commands like go forward, turn left, and steering it. And he's got some buttons that he can press that changes the mode of operation. So even though in today's demo, I would call this semi-autonomous, in that the robot is handling all its local processing, Seth is giving the high-level guidance. But we have other modes where the robot can go on its own. I'm supposed to get out of the way. So this robot can walk with a variety of gaits. Here it's walking one leg at a time. Now it's trotting, which is diagonal legs in pairs. It can also pace. If you know animals, these are all gaits named for what animals do, and we're sort of copying them. Here it's using the legs on the left and the legs on the right together. And all the coordination for that is done by the robot using that sequential composition I was talking about earlier. This robot's omnidirectional. It not only goes forward, but it can go sideways, and it can turn in place. And it can also move while it's turning in place. And it can pose its body. And the posing of the body is really important because think if you had a robot arm that was fixed, its base was fixed in space. And almost all industrial robot arms are bolted down to a table. Well, try this experiment with your own arm. How far can your hand reach? Try it at the dinner table tonight, and you'll be amazed that your arms are almost no good if you can't move your shoulder. But as soon as you can move your shoulder or even take steps, your arm has tremendous reach. And so we believe that mobile manipulation, where you have an arm on a movable body, is really a break in the paradigm and a way to make robots much more useful than they are otherwise. You know, we really like the thing in the movie that the chickens can do and that people can do, where we can hold our hands still while our body moves all around. And it represents a level of coordination and decoupling that really represents what people and animals are great at. And that is to think about the task you're doing and not worry about the details of what your muscles and your body has to do. And that's what Spot Mini's doing here. Now, this robot has a bunch of cameras on it. It has 2 on the front, which are stereo cameras. It has, when do you turn around? It has 1 on the side. Keep going. It has a butt cam. I don't know how that translates into French, but it's got a camera on the back. And it's got 1 on the other side. And can you open up the hand? And it's also got a camera in the hand, which we'll demonstrate in a couple of minutes. So using these cameras, the robot can negotiate obstacles like the stairs. We brought 1 step up here so you can see that. And the robot sees the step as it approaches, changes the pitch of the body, adjusts the stepping of the feet. It's a little bit small here because there's a gap in the back here. Another cool thing the robot can do is Seth, drive the robot right into me. He's going to put it into don't drive into him mode, so all he's doing is telling it to go forward. And when the robot detects me, it steps around. I wouldn't say the robot's completely and he's going to do it sideways too. Go ahead. So he's telling it to go sideways, but it won't go because it sees that there's an obstacle in the way, which is me. I won't quite say that it's safe and it's never going to run into anybody. We were at a trade show 2 weeks ago, and some guy blocked it and went like this, and the robot tried to go between his legs, and eventually we got it to go through, but anyway. You know, I'm feeling a little bit thirsty. Could you get me something to drink, Spot? It's not listening to my command. Seth is listening. But Seth is driving it over. But now it's in autonomous mode where it's using that camera in the hand to search for something to pick up. It found the can, and now Seth's driving it again. We have automated this whole thing, but it's a little hard to do on stage. Well, thank you, Spot. Now, Spot's a little bit of a show-off, so it's going to show you that it can do some even more dynamic behavior. It can run. And if that's not enough, it can run on 2 legs. Thank you, Spot. That's enough. Thank you, Spot. Thank you, Seth. So he's going to go down the steps frontward. Let's see if that works. Very good. Spot will be available during the break an hour from now out in the lobby. So if you want to see it up closer, or we'll give you driving lessons and you can drive it yourself. You'll see that it's very automated, and even though there's a driver, the driver's just giving instructions. Could I have the slides back? So I'm going to say a few words about 2 other robots. One is a humanoid robot we're building, and this definitely is squarely in that region of the future. We don't have ideas for immediate applications aside from entertainment for this robot, but we believe some of the work we're doing on it is really paving the way for more advanced, complicated interactions, whole body manipulation, and things like that. But before I talk about that, I wanted to say something about our philosophy of robotics. A lot of people think that robotics is you have a robot and you have a computer, and the robot sends sensory information to the computer, and the computer sends instructions to the robot, and you have some software doing that, and that's the whole story. But this is really only half the story. The other half is that the robot is interacting, especially a dynamic robot, with the physical world. And the physical world means that there's gravity pulling on the robot, which is a kind of instruction or command. There's friction, there's compliance, which means springiness, either in the world or in the robot. Almost all mechanical systems have some, and actuated systems have some compliance in them. And that means that there's energy, kinetic energy and potential energy, stored in the robot, and that acts like a command to the robot in addition to the commands that the software is doing. So we believe that you need to design this whole system that involves software and hardware design and try and come up with a harmony between how they all work. So we've been doing some work. I'm going to switch from talking about controls and software to talk a little bit about hardware design. So this is a standard robot leg. This was a big dog leg with a funny foot on it. The way we built it, where there's separate components. Here's a hose, here's some connectors, there's hydraulic actuators in here. Everything made the conventional way. And this is a concept that's supposed to look like an anatomy diagram from a biology book, where everything is more integrated and smooth. There's tissues here that have places for fluids to flow or signals to go. And that's the concept for the future. And I'll show you that we're making some progress towards this future using 3D titanium and aluminum printing, which is becoming very popular nowadays. So this is a leg part. It's right here in this humanoid. And it's got oil path. This is a cutaway, so it doesn't actually look like this, but it's got oil paths. It's got a place for an actuator here. These are places for valves. And it means we were able to take a very big, heavy item and shrink it down. It's also got some empty spaces, and shrink it down to make the robot lighter and stronger than it was just doing it the old-fashioned way with fewer connectors. And we've done that to many of the components in Atlas, our humanoid robot. The space frame is printed, which means it can be a lighter structure. This is a hydraulic manifold. We should really show it from the other side. It's just a beautiful piece of machinery that's got oil paths and places for valves and filters. That's about a third the weight of what the previous piece is, made of separate components. And this is the ultimate version of the use of this. This is a hydraulic power supply that has a motor, a pump, an accumulator, a reservoir, filters, valves, and all the communication paths. And it let us get a system that was about 4 times the volume and 3 times the weight down into a very small package so that our robot could be lighter and thereby relatively stronger than it was before. So using these techniques, we started with a robot. I'm sorry, I have this in English units, but this robot weighed about 375 pounds. That must be about 150 kilo. We were able to, in a first step, to shrink it down to about 80 kilo, and now we're down to 165 pounds, which is just a little bit lighter than me. We both have a goal of getting down to 165 pounds. I'm not quite there yet, but the robot is down there. So I'll show you a little bit of Atlas in action. This robot also has some sensors. It has a LiDAR and a stereo sensor that's used to detect these stairways, adjust its feet as it goes. And this is an outing. Again, it's very important to take these robots out in the world and test them, and that's what we do in order to develop their skills and capabilities. Here we're experimenting with whole body manipulation, not just the arms, but the torso is contributing to the motion, and the legs are also contributing to the motion. The vision system is locating the boxes. Here we're using markers on the boxes to simplify the vision. And here we're seeing if we can make the robot perform this at about human speed. And of course, if it can do it with a human, why not do it with another humanoid robot? I don't know why everybody finds that so funny. It is funny, but I don't know why. And again, part of our development technique is to test the robot in order to not just let it do its task, but figure out how to do all the adjacent tasks that are involved in having a robust solution. So here the robot is told to pick up the box, and no matter what happens, it keeps trying to do that. Could you turn down the volume a little bit? Thank you. Here we've been working on dynamic locomotion, running out in terrain, so it has to sense the terrain and adjust to it as it runs. The running isn't perfect yet, but it's getting better and better. And we're working on the kind of running you might do when you play soccer. And here's some dynamic tasks that the robot does by coordinating its dynamics. Here's a pretty tall jump. I'll bet that that's taller than half of you can jump. I certainly can't. I just have one more thing I'm going to show. You know, the name of this conference is HSI, which is sort of inspiration from unexpected places, or USI, I guess. Inspiration from unexpected places is one of the taglines. And one of the places we get inspiration is from biology. And it's important to know that we're not trying to copy biology, because we can't. You know, we have to use real engineering that's available to us. So we can take inspiration from the dynamics and balance that animals use, the compliant structures, and use that as an asset and not a liability. Whole body control, these are all things I've been talking about. On the other hand, we can't really deal with the complexity of animals, which are immensely complex compared to our robots. Right now, there's no way to use the metabolic power that animals use, and we can't fabricate the way animals do. So we are inspired by biology, but we don't really try and copy it in many cases. But I have an example where we've been inspired by biology, but we haven't tried to make the robot look like an animal. So this is a dynamic robot that has compliances in it. It's balancing, but it sure doesn't look like any person or animal that I know. It's got wheels and legs. It's not really a Segway design because the legs are independently actuated and it can lean. This is the first version of this robot. We're working on a second one that is a refinement and has some really interesting applications that are still secret, but I'll tell you about maybe a year from now. And we're excited by that. You can see it's not a Segway. It's got independently suspended legs. It can carry a heavy load. This is about, as you can see, about 50 kilo. And of course, it's a dynamic robot. So I'm out of time. Thank you very much. And I think we have time for a question or two, if you like.